Hello students, now I'm going to talk about how to do binary search. One primary assumption for binary search is we need to have a sorted array. Okay, and the objective is to see if you can find a particular element in that array. Okay, so we call it as a search key, the value that you want to search for in that array. And the way we are going to do that is um, we are going to kind of do it um, by checking whether the key is the middle element of the array first. Okay, and since the array is sorted, if the key is equal to the middle element, we are done. We have found the element in the array, so we can return that position, say m, if m is the middle index. Okay. If the key is less than this middle element, then if at all the key is located in the array, it has to be to the left of the array, right? Because if the array is sorted, so for example, let me open a new thing. Let's see, I can use the same thing. Okay, so let's say our array is going to be sorted, so it is something like this. So if you're looking for, say, 11 is the middle, so it's there. But if you're looking for, say, 7, since you first compare the key 7 with 11, and we found that the key is that we're looking for is less than 11, if at all 7 is located in this array, it has to be to the left of this, right? 11. If you're looking for, say, 17, if at all it is located in the array, once you figure out that the key is greater than this middle element, if at all it is located, it has to be to the right of it. So once you figure it out, then what you have to do is, all you have to do is basically discard, for example, if you're searching for, say, 7, then you have to basically discard the right side of the array, and of course along with this 11, so all you have to search for is on the left side of the array, and basically repeat this procedure. You can do it iteratively or recursively. Search for 7 only in this part of the array, and see again, use the same strategy, find the middle element of the array, say in this case it is 8, so compare 7 with 8. Since 7 is less than 8, if at all 7 is located in the array, it has to be to the left of the array, which is basically this one element 3. Okay, so that is an array now. And compare 7 to 3, and 7 is greater than 3, so if at all 7 is located in this array, it has to be the right of 3, but there's nothing to the right of 3, so now you can conclude that 7 is not in the array. Okay, so that is the approach we use to check whether an element is in the array or not. So I have another example here. So for example, you're searching for 70. You have the array with 13 elements. So the middle element is index 6. And how you find the index? The index is basically the m value. The middle value is L plus R over 2. So the left index plus the right index over 2. So to start with, if you have, say, a 13 element array, okay, so your L is going to be 0 and R is going to be n minus 1, so it's going to be 12. So the middle element is this floor of L plus R over 2. So in this case it is 0 plus 12 over 2 is going to be 6. So now you're comparing 70 with 55. Since 70 is greater than 55, you are now on the right side of the array. Okay. So you have to now check, you have to reset because L is no longer here. This becomes your L, index 7, and R remains the same. So your L is 7, R is 12. So 7 plus 12 over 2 is going to be 19 over 2, which is 9. So M becomes 9. Now we compare 70 with 81, and 70 is less than 81. So if at all 70 is there in the array, it should be between this position L and M minus 1. So you set your R to be M minus 1. Okay, and so L is 7, R is 8, so 7 plus 8 over 2 is 7. So your index becomes 7. So you compare 70 with 70 basically, and they're equal, so you return this index. Okay. If, as we discussed the previous example, if the element is not there, you would not be able to go to the left or right. Okay, so then you return -1. So if you look at the pseudo code, it is like start with L equal to 0, R is N minus 1, and you proceed as long as L is greater than, less than or equal to R. Okay. So every time what you do is you find the middle index, which is L plus R over 2. Okay, and if the key is the middle element corresponding to that middle index, then you return that index. Otherwise, if the key is less than this middle element, then you have to search to the left of the middle element. So like for example, if your key is less than, say for example it was 81, right, A of M, so 70 is less than 81, so what you do is you move R to the left of M, so you set R to be M minus 1. On the other hand, if the key happens to be greater than A of M, because you see it's an if else, so if the key is equal to A of M, you do this. If the key is less than A of M, you do this. If it is else, means what? Greater than A of M. So like in the first case, if the key 70 is greater than A of M, in this case is 55, what you do, which means what? If the key is greater than A of M, which means the key, if at all it's located on the right side, right? So which means you have to make your L to be M plus 1, right? That's what we do. And so if at all the key is located in the array, you will return that index. Otherwise you will return -1 when L becomes greater than R. Okay, so for example, if you're searching, say, for something like 80, okay, let's say we're searching for 80, and so we are on this side, and 80 is going to be less than 81, so we set R to be 8, L to be 7. 7 plus 8 is 15 over 2 is 7. So comparing, say, 80 with 70, and 80 is greater than 70, so we are on the right side, so we set L equals L plus 1. So we are really on this, right? So this is our middle index now, 8. 74, we are comparing 80 with 74. 80 is going to be what? Greater than 74. So if 80 is greater than 74, you have to search on the right. So you set L equals L plus 1, but R remains still the same at 8. So L becomes 9, R still stays as 8 at 8. So that is an indication that L is now greater than R. So you kind of return -1. Okay. Now, in terms of complexity analysis, the basic operation we are doing each time is comparing the key with A of M. Okay. So, how many times you are doing? When you want to search for a key, you basically look on the whole thing, right? So if the key is not equal to this, right, or less than this or greater than this, you are reducing your search space by half. Such means the number of comparisons you have to do to search for a key on an array of size n is that one comparison you do, which is this one, plus what? The number of comparisons you have to do to search for the key in half of the original array. So because you're reducing your search space by half, so this one comparison that helps you to decide whether you want to search on the left side or the right side, plus the number of comparisons you have to do to find whether that element is there or not on the right side or the left side. Let me see if I can get rid of this. Okay, so this is now just remember in the second chapter we solved a recurrence. What was the recurrence? X of n equals x of n over 2 plus 1, where x of, if if n is equal to 1, we have to do one comparison, right? Because if that element, the search key is equal to that element or not. So this is our base condition. So you want to solve this. Okay, so use n equals to the raised to k approach. You will get k plus 1. The exact problem was there in the question bank, if you remember, on chapter 2. So this is going to be k replaced with log n, so 1 plus log n, so it's going to be theta of log n. Okay, if you go to question bank for chapter 2, it should be there. I believe it was 3 instead of, yeah, I think this is a thing to look at. Instead of 3 we have 2 over there. Okay, so you get 1 plus log n to the base 2 there. Here we have log n to the base 3. So the same way you can solve this, and we did it before. Okay, all right. So let's see, where is that? Okay, so this is the complexity for binary search. It is log n, but remember, to run this algorithm, the prerequisite is the array has to be sorted, and the best time complexity that we can have to get an array sorted is going to be n log n. Okay, so this is the best complexity that you can have for a sorting algorithm. So if you consider that, it's going to be n log n to sort and log n to do the binary search. Okay, so binary search as it is will take you only log n time, but you have to have the array sorted. If you don't have the array sorted, you have to get it first sorted. So that's what is this complexity coming from, n log n. So the overall complexity is going to be n log n plus log n, which is going to be n log n in terms of theta. Okay, so you have to remember that, right? So let's look at this problem where you're trying to see how many key comparisons we need for different scenarios. So given this array, it's a 13 element array. I think it's the same thing as this one, right? Okay, good. Now look at the problem. We want to list all the keys of this array that will require the largest number of key comparisons when searched for by using binary search. Okay. Alright, so if the key is the middle element, we are going to do one comparison, right? Remember, we need at least one comparison. So it's a 13 element array, so start with L to be 0, R to be 12, so M is going to be L plus R over 2, so that's going to be 6. Okay, missing all caps here. So to search for 55, that's what I indicate here, the index is going to be 6. Okay, and if you're searching for something which is less than 55, you have to go to the left of this array, right? Okay, so which means your L, so let's construct the left subtree. So you have to really construct this tree. Okay, left subtree. So in this case your L remains to be 0, whereas R becomes 5, 1 less than this index 6, right? Okay, so M is going to be 0 plus 5 over 2, which is, remember in the pseudocode we take a floor. Okay, so that's why we have 0 plus 5 over 2, you take the floor of it, you truncate it basically, we have 2.5, so that is 2 now. So which means if you're looking for element at index 2, which is 27, you will do 2 comparisons, and if you're looking for something which is less than 27, you have to go further. In that case we have to set L equal to 0 and R equals 1, and M is going to be 0 plus 1 over 2, which is 0.5, so 0. So if you're looking for 3, you will do at index 0, you will do 3 comparisons, right? And if you're looking for something which is less than 3, it's not there. Okay, if you're looking for something that is greater than 3, but when you got to this position, it means the element you're looking for is less than 27 and greater than 3. Okay, so which means your L remains to be 0 and R is decremented, so R is going to be 1, because L is going to be 1 because the element looking for is greater than this, right? So L is going to be 1, R is going to be 1, so M is going to be 1 plus 1 over 2, which is 1. Okay, because you see here at this point we are here and we said we have R equals 1, and if the element looking for is greater than 3, it has to be at index between 0 and 2, so it has to be 1, right? So we got that, and so that is 14. So you'll do 4 comparisons. You are doing 3 comparisons here, and you compare this time here, you have 4 comparisons. Okay, and that's it. You have index 0, 1 and 2. Alright, so let's go to the right side. So to do the right side or the right subtree, you will have what? You will have your L to be 7 and R to be 12, because L is to the right of 6, so it is to be 7, and R is 12, so M is going to be 7 plus 12 over 2, that's going to be 19 over 2, so that is 9. So if you're looking for element at index 9, you'll do again 1 comparison here and then 2 second comparison here. If you're searching for something which is less than 9, So in that case, it's going to be L is going to remain at 7, whereas R is going to be 8, because you're looking for something less than 9, index 9. So M is going to be 7 plus 8 over 2, which is 7. So if you're looking for element at index 7, you'll do 1, 2, 3 comparisons. Now you're already seen at 6 and 7. So if you're looking for something that's less than 70, and if it's greater than 55, it's not going to be there, because this is a sixth element and this is index 6 and this is a seventh index 7. Okay. Now if you're looking for something just greater than 70, right, which means the left index remains the right index remains at 8, whereas the left index gets to 8, because you're looking for something that is greater than this index. So you have to shift to the right. So left index moves to 8, the right index stays at 8. So M is going to be 8 plus 8 over 2. So that makes it to be 8. Okay. And so 7, 8, 9. So if you're looking for something which is less than 74 and greater than 70, or less than 81 and greater than 74, it's not going to be basically there. Okay. Now similarly, if you're looking for something that's greater than 9, your left index should be 10 and R should be 12. So you're basically looking at something like 10 plus 12 over 2, so which is 11. So that's this index. And if you're looking for something which is less than 93, so it has to be, R has to be 10 and L is already 10, so 10 plus 10 over 2 is going to be 10, so that is this one. And if you're looking for something that is greater than 11, which means your L has to be 12, and in this case we move to the right, R is also 12, so M is 12. Okay. So that is how you construct the tree. The tree basically captures the number of comparisons you do. Okay. So now what we want to do is find the keys which have the largest number of key comparisons. Okay. So if you look at this tree, these 6 keys at index 1, 3, 5, 8, 10, 12 require the largest number of comparisons. And how many? 4, because we do one comparison, second comparison, third comparison, fourth comparison. 1, 2, 3, 4. So everywhere for any of the 6 keys in the bottommost level of this tree, you do 6 comparisons. Okay. Now there are 2 other keys, not 2 other keys, there are several other keys. This 2 keys at level 3, right? Not 2 keys, 4 keys. This key, this key, this key, and this key. So if you want to find any of these 4 keys, you will require to do 3 comparisons. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So 3 comparisons for any of these 4 keys. And if you're looking for either one of these, you will do 2 comparisons, one with the root and then one with the actual key. If you're looking for the root, you do 1 comparison. Okay, so you should be able to answer how many comparisons you do to search for any of those keys if they exist there. That's what is the B part. You want to find average number of key comparisons you do when you do a successful search. So if you look at the solution, I have 1 comparison for the key at position 6, which is the root, and the other ones. Now if you look at the question, one key assumption is assume that each key is searched with the same probability, which means there are 13 elements in this array, right? So the probability that you'll be searching for any of them is the same. Okay, so because you want to find the number of comparisons you do in general, okay, and the average number of comparisons when you search for any key. Okay, so any key could be searched for. So you have you do one comparison to search for one of these 13 keys, right? This is only one key that requires one comparison. So that's why the probability is going to be 1 over 13. And you have two keys that require two comparisons. So this is the number of comparisons. And 2 over 13 indicates that 2 of the 13 keys require two comparisons. Then 4 of the 13 keys, these 4 keys require 3 comparisons. So that's 4 of these 13 keys require 3 comparisons, and then 6 of these 13 keys require to do 4 comparisons. So that's why now when you simplify it, it is 1 times 1 1 times 1 plus 2 times 2 plus 3 times 4 plus 4 times 6 divided by 13. That's going to be 1 plus 4 plus 12 plus 24 divided by 13. So 5 plus 7, 12, 17, 17 plus 24, 41 divided by 13. Okay. Alright. Now we are going to look at find the average number of key comparisons made by binary search in the case of an unsuccessful search. Okay, when can you have an unsuccessful search? When you're looking for something that is not in this array. Now you could look for anything that is not in the array. The number of elements that you could search for which is not in the array is really uncountable. Okay. But what we can do is we can break it into intervals or ranges. You could search for anything which is less than 3. Okay, so that is this interval which is less than this index 0. And you could search for anything which is greater than 3 and less than 14, which is this interval 0 to 1. So you could break it basically into intervals like this, between 0 to 1, then 1 to 2, then 2 to 3, 3 to 4, and so on, then 11 to 12, and greater than the element at index 12. So these are the different intervals you could really break your elements. Okay, so what I mean by this again is, for example, interval 11 to 12 means you could search for anything between 93 and 98 that is not there, right? So it could search for 94, 95, 96. So everything is captured in this interval. Okay. And you could search for them equally likely. So that is again important to know. So now you go through this tree again. Okay. How many comparisons you do to search for elements in each of these ranges. So if you want to search for, say, something which is less than the index 0, you do 1, 2, 3 comparisons, right? And by the time, if you figure out that you have to move to the left, there's nothing you can move to the left, so that's 3 comparisons. Similarly, when you want to search for something that is between index elements at index 6 to 7, you do 1, 2, 3, and then you find out there is nothing you can move to the left. Okay, so for these two ranges, index 6 to 7, between 6 and 7, and less than 0, you do 3 comparisons. So that's what I state here. Okay, so for interval or range less than 0, that's one interval, and for interval index 6 to 7, for both of them you do 3 comparisons. And for the rest, what you do, if you're looking for something which is between, say, 0 to 1, you kind of do 1, 2, 3, 4 comparisons. And if it is 0 to 1 means it is greater than 3 and less than 14, right? So say 10 or something. To find whether 10 is there in this array, you have to compare with 55, then with 27, then with 3, and then it's greater than 3, so you go to the right, and then compare with 14, and now you figure out that 10 is not there, so you do 4 comparisons. Similarly, if you want to search for something, say that is say 72 or something like that, then you'll compare with 55, you compare with this, is less than 81, so you come here, is greater than 70, so come here, you're looking for 72, so 72 is less than 74, you find out there is nothing, you can move to the left because you already visited elements at position 7 and 8. Okay, so basically to compare for any of the other 12 intervals, there are 14 intervals, right? If you count this is 1, 2, 3, 4, 5, 6. So this is 13th actually, then 14th. You can really do list all of them. You'll have 14 intervals totally. So out of those 14, the 2 intervals that have 3 comparisons are this, and the remaining 12 of these 14 intervals will require you 4 comparisons. So the number of comparisons you do is 3 comparisons for 2 of those 14 intervals and 4 comparisons for 12 of those 14 intervals. So that's going to be 3 times 2 plus 4 times 12 divided by 14, which is going to be 6 plus 48 divided by 14. So that is 54 divided by 14. Okay, so you see on average you need to do like 3.86 comparisons, which is close to 4, because the majority of them require 4 comparisons, 12 of the 14. Okay, alright, thank you.